Hello everybody, welcome back to our video on 14E. This is part 2, and I noticed that I got cut off on my last video, so I just want to finish off with our example 1. So notice that when we have once we've simplified our numerator, we end up with an h in the numerator and an h in the denominator. Those h's can cancel out, and finally I'm in a state here where I'm able to substitute in 0 for h and not have a 0, not end up with my denominator being 0. So that's what I do. I can finally sub in that 0. That means I don't have to write my limit notation anymore. And I can simplify my denominator to get 2 times the root of x plus 2. Notice that when we try to calculate the derivative using the difference quotient, so when we use this version with x's instead of a's, we end up with a function in the end, a formula that helps us calculate the slope of the tangent at any point, not just the value at one point. Okay, when we plug in a, when we have a specific point and we plug in a value for a, then we'll end up with just a number at the end. Okay, and so that leads us to our next point. If I want to find the value of the derivative at a particular value, I can actually plug in that particular value of x into my difference quotient, okay, or into my derivative from first principles, and find a value for the slope of the tangent at that particular value. Okay, at points where a function is said to be differentiable at a particular value if you can find the derivative. If you can't find the derivative, then you say the derivative does not exist. Most of the derivatives that I ask you to find will be derivatives that you can find. Using the first principles formula, find the instantaneous rate of change, that's another name for the derivative, for this function at the point where x equals 5. So for example 2, we start with this definition because we have a value for x. And I'm going to start by plugging in a plus h into my formula here. That's how I got a plus h squared plus 2a plus h. I'm plugging in a plus h for x in my function, and then I'm plugging in a for my function. I'm going to substitute 5 in for a. Okay, wherever I see a, I'm replacing it with 5, and then I'm going to expand and simplify. Okay, so when I expand and simplify, I end up with 12h plus h squared over h. I notice I have a common factor of h that I can factor out. And finally, if I factor out that h, I can cancel the h in the numerator with the h in the denominator and get to a place where I can plug in or substitute 0 for h legitimately. And I end up with 12, which represents the slope of the tangent to this function at this point. Specifically, when x equals 5, the slope of the tangent is 12. Okay, the last thing I want to discuss is alternative notations. So we've been using this f prime of x notation, which was developed by Joseph Louis Lagrange, but it can also be represented, a derivative can also be represented using dy by dx. This notion was developed by Gottfried Leibniz, and it just reminds you that this is delta y over delta x, or that we're finding the limit of a slope. Okay? And we may use either notation depending on the circumstances. Your book flip-flops, and I will flip-flop as well. It's just something you do in calculus. Okay? And some background from your text, just notice that dy by dx is actually a notation, not a fraction, but we do treat it like a fraction sometimes. So you can take a look at this excerpt from your text if you'd like some more information. Thank you and have a great day. Stay safe.